right, let me just grab a chalk. So I figure we could just start with a short repetition of where we ended yesterday. And we introduced something. Did it vanish? It vanished, okay. Oh, can you hear me okay without it? Yeah. Sorry about that. So yesterday we introduced a concept known as generalized coordinates. And this was in relation to trying to obtain a description of a system with many particles, which was subject to constraints. And an example we considered was, for instance, if you have a container filled with a gas, you can think of that as a system with many particles. And then the actual constraint is that the particles cannot leave the container. So the generalized coordinates take into account constraints. And these constraints generally make the original coordinates describing the system dependent on each other. So say you have, just to use a concrete example, if you have two spheres attached to each other by a rigid bar and then also attached to the ceiling, then in principle with two particles you would have 6 degrees of freedom. They can move in 3 directions each. But then if we restrict the movement to a plane, say the blackboard plane, then you remove 2 degrees of freedom because they cannot move in and out of the plane. And then you further remove 2 additional degrees of freedom by fixing this distance, claiming that it's a rigid bar. So for this type of system, you actually have 2 degrees of freedom, which correspond to the 2 generalized coordinates. So this is just what we had a look at yesterday. And we had actually just briefly begun to derive the Lagrange equations, which are a very central concept in this course. So we'll continue this derivation today. So related to this, we introduced another concept known as a virtual displacement. Which we write like this. And you can think of the virtual displacement as an infinitesimal increase or change in the position vector of particle I, which is in accordance with the constraints that exist in the system. So this is different from a normal infinitesimal quantity, because for a normal infinitesimal quantity, which we would write just dRi, that can change in any direction. It's just a mathematical construction. Here we add some content. We actually said, okay, so this is a infinitesimal change, but it has to be in accordance with the constraints of the system. Can you see if I write here? No? Okay. And we had just begun to consider first a system in equilibrium. And what I mean by equilibrium is that the net force acting on particle I would be 0. And then we introduced a decomposition of this force. Like this. So we basically say that the total force Fi acting on particle I consists of an applied force and a force which results from the constraints in the system. So this could be, for instance, the force exerted on a particle which is inside this container if it tries to escape. Whereas this is an applied force which results from, for instance, trying to change the pressure in the gas. And so it follows that if Fi is equal to 0, then obviously the sum over all Fi's multiplied or dotted with the virtual displacement of the position vector Ri also have to be 0, because each term is 0. Okay. Now we're going to make an assumption here. So please let me know if my writing is too small for those of you on the back rows. So this is assumption. We assume that the force stemming from the constraints in the system, dotted with the virtual displacement vector, has to be 0. That doesn't necessarily mean that the actual force is 0, but at least it means that these two vectors have to be perpendicular. Now that may seem as a pretty arbitrary assumption, so could you please take 1 minute, discuss with your neighbor, and see if you can come up with an example of a situation where this is allowed, where the constraints are actually normal to the displacement vector, and see if you can also come up with an example where this is not the case. So please take 1 minute. Okay, could I have some suggestions? Let's say first for the case where this is actually the case. Yep. Sorry? Pendulum. Do you mean this one?
Just one with one bulb.
All right. Okay, so you mean oops, sorry. Something like this. Yeah, that's a very good example. So for a pendulum where we have to assume that this is rigid, that this cannot be deformed, the actual displacement vector which is allowed by constraints in the system has to be normal to this force which is keeping the pendulum in place. Do you see it? It's a very good example. Another example is actually this scenario of a gas inside of a container that we discussed. So there we have particles where the vertical displacement can only be perpendicular to the actual force exerted by the wall. So this is also a case where the force exerted by the constraints is normal to the actual vertical displacement vector, or it can be normal. Okay, what about an example where this is not the case? So in other words, a scenario where the force from the constraint is parallel to the displacement vector. Well, at least we have to exclude all scenarios including friction, because friction acts parallel to displacement. But as long as we exclude friction, this assumption is valid in a variety of scenarios. Okay, so let me now insert this decomposition of the force into our equation here. And this equation is actually something which is known as D Alembert's, I erased that, D Alembert's principle. Or alternatively, the law on virtual work. And note that this equation does not necessarily mean that the applied forces are zero. It just means that this sum, dotted with delta Ri, the virtual displacement vector, has to be zero. And it follows by making this assumption. Okay, so that was the case for an equilibrium situation. Let's now consider the case where we actually have movement or dynamics in the system. So in that case, the forces acting on particle I are not necessarily zero. But they're equal to the time derivative of the momentum of the particle. So it's just Newton's second law. Okay, so let's now make a similar decomposition of this force. It consists of an applied force and the forces resulting from constraints in the system. So we get this. And again, we'll make the assumption that the contribution from these constraint forces are zero. So we get this modified equation for the case where we do not have an equilibrium situation. So what we'll attempt to do now is to proceed with this equation and see how this actually leads up to Lagrange's equations. One thing that we discussed in the previous lecture was a classification of various types of systems in terms of what kind of constraints they had. So we introduced, for instance, something which is known as a holonomic system. The definition of a holonomic system is that the constraints in the system can be written like this. Okay, and then we'll introduce these generalized coordinates, which we also discussed in the previous lecture. The set of generalized coordinates is denoted Qi. So keep in mind that, did this vanish again? Okay. So keep in mind that the number of generalized coordinates in a system with constraints has to be fewer than the number of original coordinates. So if you have n particles with k constraints, then you have 3n minus k generalized coordinates in 3 dimensions, generally. Okay, so introducing these generalized coordinates, we can write that the original position vectors to each particle is a function of all of these generalized coordinates and possibly time. So if this is the case, then the velocity of particle I becomes it's just the usual definition, the time derivative of Ri, which I've written here in 2 ways. It can be written either explicitly by this derivation operator or with a dot on top of it. This This can then be written in the following way by using this product rule, I think it's called, for derivation. That if Ri depends on Q, you can write the total derivative like this. So the velocity of particle I becomes a function of Qi and the derivative, the time derivative of Qi, and t. In a similar way, we can write this virtual displacement like this. And note that there's no virtual displacement in time. We're only considering virtual displacements in the generalized coordinates, and there's no delta t, for instance. Okay, so if you recall now the equation we obtained for the non-equilibrium case, D Alembert's principle for the non-equilibrium case, we had two terms. We had a sum over I, and then the applied force minus the time derivative of momentum was dotted with a virtual displacement vector, should be 0. So let's have a look at the first term. And I'm just dropping the superscript A now, here. But keep in mind that this is the applied force. This does not contain the forces from constraints. So using this definition, so I'm here defining the quantity large Qj. And this also has a name. It's known as a generalized force. Okay. So we've introduced a lot of quantities and notation. So just to take one step back and remind ourselves what this represents, keep in mind that this dimension is the dimension of this is energy, because Q is a force and delta Qj has dimension length, and so force multiplied with length becomes work, which has dimension energy. Okay, that was the first term. We have this. So I just insert the definition of momentum, the time derivative of momentum here, and then I insert the definition of delta Ri, expressed through the generalized coordinates. Now I can rewrite this part of the equation. So we're assuming here that the masses of each particle, mi, they are time independent, they're constant. So if that is the case, we can rewrite this like this. So from this derivation of the total parenthesis, we get an extra term, which we're subtracting here in order to get this. Now, it turns out that we can actually interchange the time derivative operator and the derivative operator with respect to Qj. And I will not show that here, but in the compendium you have a explicit derivation of this fact. So we'll just make use of this property here. So we have this. And in a similar way, one can also show that this is allowed. That the partial derivative of the velocity with respect to the time derivative of qj is equal to the partial derivative of the position with respect to qj. So in a sense, the time derivatives here and here cancel. So you just get r and q instead of v and q dot. And this is also shown in the compendium. So we'll just make use of these properties. Okay, so if you now use these two properties and insert them into this equation, we get this. So we insert the relation on the far right side, and in addition to this relation into this equation, and end up with this. And if we now introduce, as we did in the previous lecture, the kinetic energy, well, let me write this as the sum over all the particles' kinetic energy. We get this just by inserting t here and here. Sorry. Okay, so now we have actually simplified the first and the second term in D Alembert's principle for a system out of equilibrium. So now we combine the first and the second term. And we get this. This is the contribution from the second term. And this is the contribution from the first term, where we introduce the generalized force of the system. Now, one of the virtues of introducing these generalized coordinates q is that they take into account the constraints of the system, so that they are actually independent. The original position vectors are dependent on each other if you have constraints in the system, but the generalized coordinates q take into account these constraints and thus are independent. So it means that each delta Qj in this sum is independent on each other. And if this is the case, then we can actually make a stronger statement than saying that the sum has to be 0, because each term individually has to be 0 if all the terms are independent on each other. So what we have at hand is a number of n second-order differential equations. So this is actually a quite general form of Lagrange's equations, but it's customary to reserve that notation for a conservative system. So let's see what happens with this generalized force if we, in addition to holonomic constraints, also assume that the system is conservative. For a conservative system, we know that the work performed on a particle depends only on the start and the end position. And as a result, we can write the force as a gradient of potential. So what kind of consequences does this have for the generalized force Qj? So this is just a definition, okay? Let's now insert the special form that the force has for a conservative system. So this term is actually just the product rule of derivation for this quantity. So keep in mind that the potential depends on the position vectors r. So the derivative of v with respect to q, the partial derivative, can be written like a sum, like this, since r depends on q. So if I now use the definition of Qj here for the conservative system, insert it here, and move this term over to the left-hand side, I get this. And if we make a quite general assumption once more that this potential that the force derives from is independent on the velocities in the system, but only depending on the position in the system, we can make one more simplification. So we assume that the potential energy here, it only depends on the qi, the position vectors, not the velocity vectors. And this is the same as saying that the partial derivative of v with respect to q dot has to be 0. Which means that I can add, yeah, sorry.
Do we still have a time-dependent potential?
We'll get back to that issue. Yep. So if this is 0, we can actually just add it to this equation. Like this. And let me now introduce the Lagrange function. So whereas the energy of the system is equal to the kinetic energy plus the potential energy, the Lagrange function is defined as the kinetic energy minus the potential energy. So it's T minus V. And this is probably the most central equation in this course. This is Lagrange's equations. So it's not just one equation, but it's n equations because it's one equation for each generalized coordinates, qj. And let's just remind ourselves of the assumptions we made to arrive at this result. We assumed holonomic constraints, and we assumed that the system was conservative in order to write L equals T minus V. Let me just check the time. Yeah. I'll get back to your question about the time dependence of the potential, but I think we'll take a 15-minute break.